Hi there. This is the first time that I'll be explaining my database homework in the video, so it's probably going to be a little awkward, but I'll try my best to deliver what I wrote. So let's jump straight to the problem 1. We're given a relation R equals ABCD, and we have this set of functional dependencies. A goes to BC, B to C, A to B, AB to C, AC to D, and C to A. And we're required to find the minimal cover. As we know, in order to find the minimal cover, we have to follow the 3 steps. In the first step, we have to make sure that all the right-hand side attributes are single. So for example, here we have A goes to BC. B and C can't be together when we try to find the minimal cover. We have to split them and get separate A goes to B and A goes to C. So that's the only change we make in this step. In the second step, we have to remove the extraneous attributes from the left-hand side. Attributes are called extraneous if they're not necessary for calculating a certain attribute. For example, here we have in the functional dependency AB goes to C. We already have that A goes to B, so B is already dependent on A. It's extraneous because we don't need B to calculate C. And in the second example, when AC goes to D, we already have that A is depending on C, which means A is extraneous in here too. So we're removing the extraneous attributes, and we get A goes to B, A to C, B to C, A to B, A to C, C to D, and C to A. And in the final third step, we have to eliminate the redundant functional dependencies. A goes to C is a redundant functional dependency in this case, so we remove that, and also we have a duplicate of A goes to B. We also remove that, and the remaining functional dependencies are B goes to C, A goes to B, C to D, and C to A, and that set of functional dependencies is our minimal cover. So that's that for the part A. On the part B, we have to find all candidate keys by closure attributes. As we know, candidate keys, their closures have to contain all the attributes that are in the initial relation. So for example, A's closure is ABCD, and it contains all the attributes in the initial R. That means A is a candidate key. For B as well, its closure is BCAD, and B is also a candidate key, and C's closure is CABD, and C is a candidate key. And the way we find the closure is simple. So C's closure is, we see that C goes to D, C goes to A. So we have C goes to A, so we take CA, and then A goes to B, and then we take B, and then B goes to C, and then the next C goes to D. So we have CABD. That was just an example, and we see that all A, B, and C are A candidate keys. However, D's closure is only D because we don't have any attributes depending on D, and that's why D is not a candidate key. And that's it for the problem 1. In problem 2, we have to explain what is a lossless decomposition and what's the formula to determine whether a decomposition is lossless or lossy, and okay, the answer. If we have a relation decomposed into sub R1 and R2 relations, its decomposition is called lossless. If, so let's say we have an initial table and we try to split it into several relations. Let's say R1 and R2. So if we try to reconstruct that initial relation by the join function, we have to get the exact same relations, and we can't have missing data. If we get at least one missing data, then the decomposition is not lossless. However, there is a formula to check whether the decomposition is lossless or not. So it is lossless if the following conditions satisfy. The first one is if we take the union of those two relations, we have to get R, which was the initial relation. It means all attributes have to be there. Then if we take the intersection of those two sub-relations, it cannot be null. So we have to have at least one common attribute in their intersection. And the final condition is that if we take their intersection, we have to get the superkey of either R1 or R2. If any of these conditions does not satisfy, then it's lossy, not lossless. Okay, problem 3. We're given the relation R is equal to A, B, C, D, E, and the set of functional dependencies A goes to B and B, C goes to D. We have to convert it to 3NF. As we know, the first step of converting relation to 3NF, we have to find the minimal cover. And following the same steps for finding the minimal cover as it was in the problem 1, we obtain the same functional dependencies because there are no changes to be made, and we get A goes to B and BC goes to D. The set of attributes missing on the right-hand side of any functional dependencies are A, C, E, because in the right-hand side we only have B and D. So AC is a super key, and therefore it's the only candidate key. Now we have to check for the we have to check if any of the functional dependencies actually violate the 3NF conditions. We take the first one, A equals to B. It does violate since the left-hand side is not a super key, and therefore we obtain the subrelation AB. Then we check the BC goes to D, and again we see that it violates with the same reason. The left-hand side is not a super key, and then we obtain the table BCD. Then we add it to our candidate key, the normalized 3NF table set, to the following table, which is ACE, and we achieve the set of our subrelations R1, R2, and R3 that contain AB, BCD, and ACE. So that's that for the part 1, and then in the part 2 we have the exact same relation, and we have to convert it to BCNF. And then we have to check if the decomposition is lossless and if it's preserving. Yeah, right. So in the step 1 we have to find the minimal cover that we already did in the previous exercise. Which is A goes to B and BC goes to D. So let's denote this relation, this initial table as R1. And then BCNF algorithms wants us to check if the initial table is already in BCNF. So we check it, it's not, because A goes to B functional dependency violates the BCNF condition as the left-hand side is not a super key. And then we have to split the initial table into two separate relations, R2 equals AB and R3 equals ACDE. And so we check if is R2 a BCNF. It is, because it does not violate the conditions. And then we, because left hand side is a super key. And then when we check the R3, we see that AC goes to D violates. The left-hand side is not a super key, and it violates the condition of BCNF. So we have to take that in, take R3 and split it into two subtables, R4 and R5. So R4 is ACD and R5 is ACE. When we check both of these tables, they both satisfy the condition of BCNF. So we have our finalized BCNF form as a set of three subrelations: R2 equals AB, R4 equals ACD, and R5 equals ACE. And now let's check the dependency preservation and see if it's lossless. Okay, we have our R2 is A goes to B, and we have our R4 is AC goes to D. However, we lost BC goes to D functional dependency, and therefore it's not a dependency preserving decomposition. Since we lost data, it can't be lossless. We'll talk about this problem a bit more when we discuss the problem 5. Okay. Okay, problem 4. We have to convert the following to BCNF and check if it's lossless and its dependency preservation, underlying primary keys of the decomposed relations. Okay, so we have car that contains this following attributes: serial number, model, brand name, body style. I denoted these attributes as ABCD just not to overwrite this names. So we also have the set of this functional dependencies. Model goes to brand name, model goes to body style, and serial number goes to model. So in other words, B to C, B to D, and A to B. We have to first of all, we transform it to its canonical form, and we get B goes to CD instead of B goes to C and B goes to D. So we have B goes to CD and A to B. And our minimal cover is B goes to CD and A goes to B. We see that only A is not in right-hand side. That means every candidate key must contain A. A is a super key, and therefore it's the only candidate key. Now we have to check whether the initial table is in BCNF. It's not, because the functional dependency B goes to CD violates the BCNF, as the left-hand side is not a primary key. We split the table, our initial table, we split it into R1 and R2 containing B, CD, and AB. So we check if R1 is in BCNF. It is, because B becomes a super key, and therefore it satisfies the BCNF condition and is in BCNF. And when we check the R2, it also satisfies, because A is a super key for R2. It's a primary key for R2. So for underlining the primary keys, it has to be B for R1 and A for R2. In other words, in the initial problem, it was B goes for a model and A is the serial number. So we have model and serial number as primary keys in R1 and R2 subrelations. Then for checking the dependency preservation, we have that initially we had B goes to CD and A goes to B, and now we again have B goes to CD and A goes to B. That means we did not lose any data, and therefore the decomposition is dependency preserving. And now let's check if it's lossless by the formula. As we know, the third step of the third condition of the formula for being lossless decomposition, it was that the intersection had to contain a superkey of either of these subrelations. So here we have R1's intersection with R2 equals to B, which is a superkey for the R1, and therefore it is a lossless decomposition. And B was the model, so yeah. I guess that's it for the problem 4. Moving on to problem 5. So we have to answer to the following question: why we may prefer 3NF over BCNF. So even though 3NF is less stronger than BCNF, and it whatever is contained in 3NF, it's also contained in BCNF. However, there are some cases that 3NF is more preferable than BCNF. So I'll mention 2 reasons as I wrote in this homework. The first one is that 3NF is much easier than BCNF. It's easier to achieve. Because when the functional dependencies get more complicated and complex, BCNF algorithms becomes pretty hard to achieve, and comparatively 3NF is much easier. And the second reason is that 3NF guarantees a lossless decomposition, so you can technically get a lossless decomposition when you convert it to 3NF. when we convert to 3NF. However, when we do the same thing for BCNF, we might not get a lossless decomposition.